Hydrothermal vents in particular and our study site, it's 1.5 miles underwater. So there's a lot of water separating what's going on at the surface to what's going on in the deep. And so the currents are really calm down there. There's some tidal influences and planetary influences, but what you see in terms of the strong storms and impacts at the surface, you don't generally think about in the deep. And beyond that, it's very cold, there's no light. And at Hydrothermal Vents, you have a very unique community of animals that are living there. And these animals don't rely on photosynthetic products, so anything that involves photosynthesis to make their carbon. Instead, they use chemosynthesis. So even in some places in the deep sea where you might have a seasonal input of food, we don't have that at Hydrothermal Vents. So hydrothermal vents in particular, and the deep sea in general, really are thought of being disconnected from the surface ocean and the atmosphere. But what we found is that there are large mesoscale eddies that are generated by atmospheric forcing. Basically, you have wind jets that are going through mountain gaps in Central America and forming these huge eddies. And they can actually penetrate all the way into the deep sea and move animals and move all the chemicals that are coming out of these really hot vents. So you have an atmospherically forced mechanism, something that's seasonal, that's subject to things like El Nino, that's affecting what's going on in the deep sea in general, and specifically we show at hydrothermal vents. So mesoscale eddies are characterized by the fact that they're swirling. You can kind of think of an equivalent in the atmosphere would be a hurricane or a really big tornado. And when I say really big, that's because these are hundreds of kilometers across, so hundreds of miles across. My original question was for my graduate thesis, and it was try to understand how larvae, the kind of babies of the organisms that live at vents, get from one vent to another. And this is really important because hydrothermal vents are distributed on the mid-ocean ridge and where other regions where you have new oceanic crust being formed. So they're very volatile systems where you have eruptions, volcanic eruptions and earthquakes that could devastate communities on a pretty frequent basis in this area. So about on a decadal timescale. So if you wipe out a community, how do you get new animals to that community? So understanding how these larvae get from one place to another is really important. And we had no idea how they could get from one vent to another, which could be separated by up to hundreds of kilometers. So to do that, it's very difficult to study larvae in general in the ocean because larvae are about the size of a pencil tip or even smaller in some cases. And the ocean's really big. So that poses a first challenge. But there's also a second challenge in that our study site at 9 degrees north on the East Pacific Rise is at least 500 miles away from the coast. So it's a pretty remote location. So in order to do this study, we put out moorings that we could leave at the bottom of the ocean, and they were equipped with current meters to look at what the currents were doing in the fluid flow, and also sediment traps, which is essentially big cones that collect any settling particles. So they're going to collect any chemicals that are falling down and also any larvae that are settling towards the bottom. And it was a big surprise when we looked at it and we saw that near the end of our time series, we saw a huge drop in the flux of the larvae coming in and also a drop in the chemicals. And that happened to coincide with a period when the currents actually increased in velocity and were very dynamic. And not being a physical oceanographer myself, I went to a colleague who was a co-author in the paper, and he's like, well, that looks like an eddy. And we looked at, for satellite evidence, whether or not at the surface there was an actual eddy. And then to be able to tie the surface to 1.5 miles below it, we used HICOM modeling. So we used model simulations to show that when you actually do have these eddies at the surface, the prediction is to have strong and coherent currents in the deep, similar to what we saw on the ridge axis. This is showing the sea level anomalies as measured by satellite observations in our study region off of the coast of Central America. The mesoscale eddies that we're interested in are in red, And as we watch the video, you can see off of the coast of Mexico, there's a yellow and then orange and red eddy, a circle that's now crossing the ridge and impacting the site. This video shows the model simulations, and here we're showing in colors again, similar to the first video. In red, you have a positive sea level anomaly, and those are the mesoscale eddies that we're interested in. But additionally, the black arrows show the predicted or modeled bottom currents that we would expect to see from our observations. And so if you hit play, you can see that at the beginning there aren't a lot of currents, but you develop very strong and coherent currents as the eddies pass our site.